Welcome to For Science Salah Lotfy channel, where science meets curiosity. في هذه القناة لا نكتفي بعرض الأبحاث العلمية، بل نترجمها إلى المعرفة التي تصل إليك أينما كنت. Our mission is to make global scientific research understandable, accessible, and multilingual. جميع الفيديوهات العلمية هنا مترجمة إلى اللغة العربية، بالإضافة إلى لغات عالمية أخرى. French, Spanish, German, Urdu, and more. Because science speaks every language. نعم، العلم يتحدث بكل اللغات، ونحن نحرص أن يصلك بلغتك. If you're passionate about science, you're in the right place. اشترك الآن وابدأ رحلتك مع العلم خطوة بخطوة. For Science Salah Lotfy channel, العلم للجميع.
Welcome to For Science Salah Lotfy channel. Today we explore groundbreaking research combining nuclear engineering with artificial intelligence. The study is titled Reactor Net, based on machine learning framework to identify control rod position for real-time monitoring in PWRs. Control rods are the backbone of reactivity control in every nuclear power plant. Traditionally, monitoring rod positions depends on physical sensors and measuring devices. But what if those sensors fail? The consequences could be critical. This is where artificial intelligence comes into play. The research introduces Reactor Net, a machine learning framework designed to identify exact control rod positions in real time. Using deep learning algorithms, Reactor Net analyzes reactor data with remarkable accuracy, creating a smart layer of digital intelligence that continuously monitors reactor operations. The implications for nuclear safety are profound, reducing human error and adding crucial redundancy. It supports safer, more reliable reactor operations with real-time reactor dynamics. In a world where nuclear energy plays a vital role in clean power generation, frameworks like Reactor Net represent not just advancement but necessity. Thank you for watching For Science Salah Lotfy channel. Stay with us as we explore the cutting edge of science and technology. Welcome to For Science Salah Lotfy channel. In this episode we present a groundbreaking study published in Scientific Reports, Volume 15, Article number 30173, in the year 2025. The research is titled Reactor Net, based on machine learning framework to identify control rod position for real-time monitoring in PWRs. This research brings together a distinguished team of scientists from leading Egyptian institutions, combining expertise in nuclear engineering, computer engineering, artificial intelligence, and avionics. Let us first recognize the researchers. Professor Dr. Ahmed Omar, Nuclear Engineering Department, Military Technical College. Professor Dr. Mohamed Elhadad, Department of Computer Engineering and AI, Military Technical College. Professor Dr. Mohamed El-Samra, Nuclear Engineering Department, Military Technical College. Professor Dr. Tariq Nagla, Nuclear Engineering Department, Faculty of Engineering, Alexandria University. Professor Dr. Tamer Makawi, Avionics Department, Military Technical College. At the heart of the study lies one of the most critical components in a nuclear reactor, the control rods. These rods regulate the nuclear chain reaction by absorbing neutrons, and their position directly determines the safety and stability of the reactor. Traditionally, the position of these rods is tracked using physical measurement devices, but sensor failures or inaccuracies can pose serious risks. To address this challenge, the researchers developed Reactor Net, a machine learning framework capable of identifying control rod positions in real time for pressurized water reactors. Using deep learning algorithms, Reactor Net analyzes reactor operational data, providing accurate predictions of control rod positions even under complex and dynamic conditions. Compared to conventional monitoring systems, this AI-powered framework adds an advanced layer of intelligence and reliability. It ensures operators receive real-time, precise information, reducing human error and strengthening overall nuclear safety. The study demonstrates how artificial intelligence can become an essential partner in the operation of nuclear power plants. By enhancing monitoring accuracy, Reactor Net not only protects reactor performance, but also safeguards against potential accidents, ensuring a safer future for nuclear energy. This innovative work, published in Scientific Reports 2025 Volume 15 Article 30173, highlights the power of collaboration between nuclear engineering and artificial intelligence. We congratulate the research team, Professor Dr. Ahmed Omar, Professor Dr. Mohamed Elhadad, Professor Dr. Mohamed El-Samra, Professor Dr. Tariq Nagla, and Professor Dr. Tamer Makawi, for their valuable contribution to advancing nuclear safety. Thank you for watching For Science Salah Lotfy channel. Stay with us as we continue to share the latest breakthroughs in science and technology. Welcome to For Science Salah Lotfy channel. Today we're diving into a cutting-edge research paper published in Scientific Reports, 2025, Volume 15, Article 30173. The study is titled, Reactor Net based on machine learning framework to identify control rod position for real-time monitoring in PWRs. This research introduces a novel framework called Reactor Net, combining nuclear engineering and artificial intelligence to ensure the safe and efficient operation of pressurized water reactors, or PWRs. In our modern world, the demand for energy is relentless and growing. As nations develop and populations expand, our collective need for electricity is projected to skyrocket. The challenge is monumental. How do we meet this soaring demand while simultaneously combating climate change by drastically reducing our carbon emissions? Renewable sources like solar and wind are vital components of the solution, but they face challenges of intermittency and energy storage, meaning they can't always provide power when it's needed most. This creates a critical need for a clean, reliable, and powerful energy source that can operate 24/7, providing the baseload power that underpins our entire infrastructure. For many, nuclear energy is the answer. Its unparalleled energy density and ability to generate massive amounts of carbon-free electricity make it one of the most important tools we have. But with this immense power comes an equally immense responsibility. Public trust and the viability of nuclear power depend entirely on one single non-negotiable principle: safety. The philosophy of nuclear safety is built on the concept of defense in depth, a multi-layered system of redundant protections. The very first and most fundamental layer of this defense lies at the heart of the reactor itself, the precise control of the nuclear reaction. Inside the core, fuel rods containing uranium-235 are bombarded by tiny particles called neutrons. When a neutron strikes a uranium nucleus, it splits in a process called fission, releasing a tremendous amount of heat and, crucially, more neutrons. These newly released neutrons can then go on to split other uranium atoms, creating a self-sustaining chain reaction. The key to harnessing this incredible power for electricity generation is to maintain this chain reaction in a perfectly stable, controlled state. This is where control rods play their critical role. In a pressurized water reactor, or PWR, control rods are the primary means of regulating the fission process in real time. They are made of materials like boron, cadmium, or hafnium, which are exceptional neutron absorbers. Think of them as sponges for neutrons. When lowered into the reactor core, they soak up the free neutrons, effectively removing them from the chain reaction and slowing it down. When they are withdrawn, more neutrons are available to cause fission, and the reaction speeds up. By making minute adjustments to the position of these rods, operators can achieve a state known as criticality, where the chain reaction is perfectly balanced and self-sustaining, producing a steady, predictable output of power. But the control rods don't work in isolation. PWRs are engineered with powerful, inherent safety features. One of the most important is the negative temperature coefficient of the coolant. The water in a PWR acts as both a coolant to transfer heat and a moderator to slow down neutrons, making fission more efficient. If the reactor's power increases and the water gets hotter, it becomes less dense. This less dense water is a less effective moderator, so it slows down fewer neutrons, which in turn automatically slows the rate of fission. It's a passive, self-regulating feedback loop that naturally prevents runaway power surges. Furthermore, operators use a secondary system, dissolving boric acid into the coolant. Boron is a potent neutron absorber, and by adjusting its concentration, operators can manage long-term changes in the reactor's behavior, like compensating for fuel burnup over many months. A miscalculation in control rod position, coolant temperature, or boron concentration could lead to dangerous power surges or overheating. Therefore, the constant, precise monitoring of all these interconnected parameters is absolutely essential for the safe and reliable operation of a nuclear power plant. At the heart of every nuclear reactor is a controlled chain reaction, and the key to managing it is understanding the thermal neutron flux. This is the flow of low-energy neutrons that trigger fission and generate power. Traditionally, monitoring this vital sign has relied on an array of physical sensors placed directly inside the reactor core. These devices, often self-powered neutron detectors or miniature fission chambers, are our eyes and ears inside one of the most extreme environments on Earth. They are essential, but they come with a set of profound limitations that have challenged the industry for decades. The first major challenge is one of coverage. For practical reasons, cost, complexity, and the need to maximize space for fuel, only a limited number of these sensors can be installed. They are housed in fixed instrumentation tubes, meaning we get data from only a few dozen discrete points within a core that might contain hundreds of fuel assemblies. This creates a problem of low spatial resolution. It's like trying to understand a masterpiece painting by looking at just a handful of pixels. You might get the general color scheme, but you miss all the critical details, the subtle textures, and the true picture of what's happening. Vast regions of the core go unmeasured, and their conditions must be estimated by computer models, introducing a significant layer of uncertainty right where it matters most. Secondly, the reactor core is an incredibly hostile environment. Sensors are constantly bombarded by intense neutron and gamma radiation, while enduring temperatures over 300 degrees Celsius and immense pressure. This relentless assault takes its toll. Over time, the very materials of the sensors degrade. Radiation can alter their atomic structure, causing their electrical properties to change. This leads to a phenomenon known as signal drift, where the sensor's output becomes progressively less accurate. To compensate, reactors require frequent and costly recalibrations, often forcing a complete shutdown. Furthermore, the data that is collected is often processed through complex physics codes that can be slow to run. This delay means operators are often looking at a slightly outdated picture of the core, potentially missing the subtle early-stage anomalies, like localized power fluctuations or the initial signs of fuel wear, that could foreshadow larger problems. Ultimately, these challenges converge on the control room, creating a persistent fog of war for the reactor operators. They are tasked with making rapid, high-stakes decisions based on data that is sparse, potentially inaccurate, and slightly delayed. To ensure safety in the face of this uncertainty, operators are forced to maintain wide safety margins. This means running the reactor more conservatively, often at a reduced power level, to create a buffer against the unknown. While this prioritizes safety, it comes at a direct economic cost, reducing the plant's overall efficiency and power output. The limitations of traditional monitoring don't just represent a technical problem, they create a fundamental operational constraint, forcing a trade-off between knowledge, safety, and performance. Thermal neutron flux is essentially the heartbeat of a nuclear reactor. Small irregularities in this neutron flow can indicate malfunctioning fuel assemblies, uneven power distribution, or early warning signs of safety issues. By imaging and analyzing neutron flux in real time, scientists can detect problems early and respond before they escalate. Faced with the challenge of monitoring the invisible dance of particles inside a nuclear reactor, a new approach was needed, one that could see beyond the limitations of individual sensors. This is where Reactor Net comes in. It represents a paradigm shift, moving from a collection of disparate data points to a single, holistic understanding of the reactor's core state. At its heart is a clever use of existing non-invasive technology. The framework starts with data from X-core detectors, sensors outside the reactor vessel that capture the thermal neutron flux. This flux, the distribution of slow-moving neutrons sustaining the chain reaction, creates a unique fingerprint of the reactor's state. This data is processed into 2D images, providing a visual snapshot of core activity. By training on thousands of these images from high-fidelity simulations, Reactor Net learns to decipher subtle patterns within this neutron fingerprint. Patterns far too complex for a human to interpret directly. So how does it work? The foundation is a powerful neural network called EfficientNet B0, chosen for its balance of high accuracy and computational efficiency, making it ideal for real-time use. The true genius is its deployment in a hybrid system that performs two tasks from one input image. The first is classification. Like sorting, it determines the category of the reactor's state. The second is regression. Like measuring, it predicts precise numerical values for key parameters. This dual capability is what makes Reactor Net so uniquely powerful. Let's look at classification. A critical factor for control is the precise position of the control rods, the primary brakes on the nuclear reaction. By analyzing the neutron flux image, Reactor Net classifies the rod configuration with an astonishing 97.5% accuracy. This gives operators immediate, reliable confirmation of the reactor's mechanical state, enhancing safety and helping to prevent anomalies before they escalate. Simultaneously, the regression network predicts a suite of crucial parameters. This includes boron concentration in the coolant, a secondary chemical control, as well as the coolant's density and moderator's temperature, which impact the chain reaction's efficiency. Most impressively, Reactor Net provides a real-time estimate of net reactivity, the overall tendency of the neutron population to change. This transforms control from a reactive process based on delayed calculations to a proactive one based on immediate insight. This is all achieved through a unified multi-output framework, a stark contrast to traditional methods that rely on a complex web of separate sensors and slow simulations. Those systems suffer from data lag and potential sensor failure, creating an incomplete picture. Reactor Net, deriving all insights from one data source, provides a coherent, self-consistent, and instantaneous snapshot of the reactor's health. It's a more robust, elegant, and ultimately safer way to manage nuclear energy. Reactor Net processes neutron flux images and applies advanced techniques, principal component analysis and clustering analysis, to decode variations in neutron flux caused by control rod movements. Test time augmentation and cross-validation techniques ensure robust performance under various reactor operating conditions. The system provides continuous automated monitoring with immediate alerts for any anomalies or safety concerns. This breakthrough represents a significant advancement in nuclear reactor safety and efficiency monitoring. The research demonstrates the powerful potential of artificial intelligence in critical infrastructure safety. Reactor Net's ability to provide real-time, accurate monitoring could revolutionize how we ensure nuclear reactor safety worldwide. As we continue to rely on nuclear energy for clean power generation, innovations like Reactor Net will be essential for maintaining the highest safety standards. Thank you for joining us on this deep dive into cutting-edge nuclear engineering research. Reactor Net represents just one example of how artificial intelligence is transforming critical scientific fields. If you enjoyed this scientific exploration, please subscribe and hit the notification bell for more cutting-edge research content. Welcome back to the channel. Today, we're venturing deep into the heart of nuclear power generation to explore Reactor Net, a groundbreaking AI framework poised to revolutionize how we monitor and control nuclear reactors in real time. For decades, reactor operators have relied on a combination of physical sensors and complex, time-consuming computational models. These models, while incredibly detailed, can take hours to run, creating a delay between the reactor's actual state and the operator's understanding of it. This inherent latency is a significant challenge in an environment where split-second decisions are paramount. Reactor Net challenges this old paradigm by closing that gap, offering not just a snapshot of the present, but a predictive glimpse into the immediate future of the reactor core's behavior. By the end of this series, you'll understand not only how Reactor Net works, but why it represents a fundamental leap forward in nuclear safety and operational efficiency. This isn't merely an upgrade to existing systems, it's a redefinition of what's possible. We're talking about a system that could help prevent accidents by identifying dangerous precursors long before a human operator could, optimize fuel consumption to make nuclear energy more economical, and ultimately, build a new foundation of trust in the safety and reliability of nuclear power. So, let's begin by exploring the fundamental physics that Reactor Net has been trained to understand. At the core of any reactor's operation are the control rods. Think of them as the ultimate power regulators, or the brakes of the nuclear chain reaction. Typically made from materials with a high neutron absorption cross-section like boron, cadmium, or hafnium, their job is simple yet critical: to soak up free neutrons. When you insert the control rods deeper into the reactor core, they absorb more neutrons, which means fewer neutrons are available to cause further fission events. The chain reaction slows and power output decreases. Conversely, when you slowly withdraw the rods, more neutrons are free to sustain the reaction and power ramps up. This delicate dance of insertion and withdrawal allows operators to precisely manage the reactor's power level. It's this fundamental relationship between rod position and reactivity that forms the first pillar of the data used to train Reactor Net. To build a truly intelligent system, the researchers needed a comprehensive dataset that captured the full spectrum of reactor behavior. They meticulously generated 80 case studies, each representing a unique operational state. The first variable was control rod position, tested at 5 key insertion levels, fully withdrawn at 0%, then 25%, 50%, 75%, and finally, fully inserted at 100%. But rod position is only part of the story. They also varied the concentration of boric acid in the coolant. Boron acts as a chemical shim, a soluble neutron absorber that provides a slower, more uniform method of control across the entire core. Finally, they factored in coolant density. In most reactors, water acts as both a coolant and a moderator, slowing neutrons to the optimal speed for fission. As the water heats up, its density decreases, making it a less effective moderator and naturally slowing the reaction, a crucial negative feedback loop for safety. By systematically varying these three critical parameters, rod position, boron concentration, and coolant density, the researchers created a rich, multidimensional data set for the AI to learn from. The combined effect of these parameters is measured by a single, crucial value, reactivity or K-effective. This value tells us the state of the chain reaction. A K-effective of exactly 1.0 means the reactor is critical, the neutron population is stable, and power is constant. Below 1.0 is subcritical, where the reaction is dying out. Above 1.0 is supercritical, where the reaction is growing and power is increasing. Let's look at a concrete example from the training data. In a scenario with 800 parts per million of boron and the control rods fully withdrawn, the reactivity hit 1.04. This slightly supercritical state is typical during a controlled power increase. In contrast, with the rods fully inserted and a higher boron concentration, the reactivity plummeted to 0.98. In this subcritical state, the reactor is safely shutting down, with each generation of neutrons smaller than the last. Now, monitoring every single point within a massive reactor core is computationally prohibitive, even for an AI. To solve this, the researchers leveraged a key design feature of many reactors: symmetry. The core is often designed in 4 identical quadrants. The physics in one quadrant mirrors the others. Therefore, instead of monitoring the entire core, they focused their instrumentation on just the top right quarter. Within this quadrant, they used the readings from 17 strategically placed in-core neutron detectors. These physical sensors provide the ground truth, the real-world data that tells the AI exactly what is happening inside the core. This intelligent simplification dramatically reduces the computational load without sacrificing accuracy, making a real-time system feasible. The data from these 17 detectors is used to generate a neutron flux map, essentially a heat map that visualizes the concentration and intensity of neutron activity across the quadrant. Bright red hotspots indicate areas of high fission rates and power generation, while cooler blue areas show lower activity. These maps provide an intuitive and detailed picture of the core's state. For instance, as animated control rods insert deeper into the core on these maps, you can see the hotspots around them dim and cool, a direct visual confirmation of neutron absorption. The ultimate goal of Reactor Net is to learn the complex, non-linear relationship between the inputs, rod position, boron, coolant density, and this detailed flux map. It must be able to predict the entire heat map instantly and accurately for any given set of conditions. To understand the power of Reactor Net, we must first understand what it sees. This 3D simulation shows the neutron flux inside a reactor core, the lifeblood of the nuclear chain reaction. As control rods, which are made of neutron-absorbing materials like boron or cadmium, are inserted, they create distinct zones of flux suppression. These are not simple shadows, they are complex, three-dimensional patterns that shift and evolve based on rod position, fuel burnup, and coolant conditions. For a human operator, interpreting the sparse readings from a few dozen sensors to build a mental model of this entire volume is an immense cognitive challenge. But for an AI, these intricate flux distributions are data. Reactor Net is trained to recognize these patterns, learning the subtle signatures that correspond to specific operational states. It learns the physics of neutron absorption not from equations, but from observing these visual consequences, much like a human learns to recognize faces. This foundational capability of spatial pattern recognition is what allows the AI to move beyond simple monitoring to genuine understanding. But real-world reactor data is far from the pristine environment of a simulation. Sensors are messy. To prepare Reactor Net for the complexities of a live operational environment, researchers began by systematically degrading the clean simulation data. They introduced Gaussian noise, a statistical model that effectively simulates the random, persistent background interference from electronic components and thermal fluctuations. This is just the beginning of simulating reality. Real sensors can also fail intermittently, producing sudden spikes or flatlining completely. They can suffer from calibration drift over long periods where their readings slowly become inaccurate. By training on data that includes these simulated imperfections, Reactor Net becomes robust. It learns to distinguish between a genuine anomaly in the reactor's state and a simple sensor malfunction, a critical feature for preventing false alarms and building operator trust. The model must learn to see the true signal through the noise, a task that is fundamental to its reliability. Before training the AI, the research team performed a thorough exploratory data analysis, or EDA, to understand the fundamental characteristics of their dataset. This is like a detective gathering clues. They examined the distributions of key operational parameters. For instance, the concentration of boric acid, a soluble neutron absorber used for fine control, was found to cluster tightly around 1200 parts per million. This is a typical value for a pressurized water reactor, or PWR, during its mid-cycle operation, providing a baseline for normal conditions. Similarly, the primary coolant temperature centered near 310 degrees Celsius, the optimal operating point for efficient heat transfer while maintaining a safe margin from boiling. Finally, reactivity, the measure of the chain reaction's stability, followed a perfect normal distribution centered precisely at 1.0. A reactivity of 1.0 signifies a critical state where the neutron population is stable and the reactor is generating power at a constant rate. The narrowness of this distribution confirmed the dataset represented a stable, well-controlled operational period, making it an ideal foundation for training the AI on what normal looks like. The analysis then moved to correlations, seeking relationships between variables. A correlation analysis revealed a moderate positive correlation between coolant density and reactivity. This might seem counterintuitive, but it reflects a core principle of reactor physics. In a PWR, water acts as a neutron moderator, slowing down fast neutrons so they are more likely to cause fission. Denser coolant, which is typically colder, is a more effective moderator. It slows down more neutrons per unit volume, which in turn increases the rate of fission and thus reactivity. This phenomenon, known as the negative temperature coefficient, is a crucial inherent safety feature. If the reactor gets too hot, the water becomes less dense, moderation decreases, and the reaction automatically slows down. By identifying this relationship in the data, the team confirmed that the simulation accurately captured these fundamental physics, giving them confidence in the data's fidelity. With a deep understanding of the data, the next phase was preparation and pre-processing, a meticulous process of cleaning and structuring the data for the AI model. This began with outlier filtering, using statistical methods to identify and remove data points that were likely the result of sensor errors or transient events not representative of the core physics. Next was variable encoding, converting categorical data, like which control rod bank is moving, into a numerical format the AI can understand. Then came normalization. Variables like temperature, measured in hundreds of degrees, and boron concentration, measured in thousands of parts per million, exist on vastly different scales. Normalization rescales all variables to a common range, typically 0 to 1, ensuring that no single feature can disproportionately influence the model's learning process. Finally, for the flux map images, the team used data augmentation. They created new training examples by applying slight rotations, shifts, and flips to the existing images. This teaches the model to be invariant to these minor changes, making it more robust and generalizable to real-world conditions where sensor alignment might not be perfect. The result of this rigorous process is a system that stands in stark contrast to traditional monitoring. For decades, reactor control has relied on operators interpreting a limited number of discrete data points from sparse sensors, supplemented by periodic offline physics calculations. It's a system that works, but it's reactive and places immense cognitive load on the human operator. Reactor Net, on the other hand, performs data fusion. It learns the complex, non-linear relationships between hundreds of inputs simultaneously. It doesn't just report numbers, it learns the underlying flux patterns and from them, predicts critical parameters like boron levels, coolant temperature, control rod positions, and overall core reactivity in real time, with a full 3D spatial understanding. This isn't just an incremental improvement in monitoring, it's a fundamental paradigm shift in reactor operation and safety. By transforming a flood of raw signals into clear, actionable insights, Reactor Net moves control from a reactive to a proactive stance. An operator can now ask, what if? What will happen to the flux distribution if we move this control rod bank in 10 minutes? The AI can provide a highly accurate, predictive answer, allowing for optimized performance and enhanced safety margins. It can spot the faint early signature of a developing issue, like a xenon oscillation, hours before it would become apparent on traditional instruments. This fusion of deep domain knowledge from nuclear engineering with the pattern recognition power of cutting-edge AI represents the future of complex industrial control. By meticulously preparing the data and understanding its physical meaning, researchers have built a tool that promises to make nuclear energy safer and more efficient than ever before. Thanks for watching. If you found this deep dive insightful, please like, subscribe, and share it with fellow science and technology enthusiasts. Until next time, stay curious and stay safe.
Where UAB denotes a uniform distribution between A and B, these augmentations introduced variability in the input data, especially beneficial for improving generalization in the classification components of the model. We initially experimented with Vision Transformer and ResNet 50 architectures, both known for their success in standard image classification tasks. However, these models underperformed in our multi-output setup. VIT applies self-attention mechanisms across images, allowing it to capture global relationships effectively. While VIT showed strong performance in capturing global relationships, it ultimately struggled with localization and consistency in our multi-output scenarios. The deep residual layers in ResNet 50 facilitate gradient flow and allow the network to learn highly detailed local features. Based on the limitations observed, Efficient Net B0 was chosen due to its compound scaling, which balances depth, width, and resolution for enhanced efficiency without sacrificing performance. Efficient Net B0 is fine-tuned to address multi-output tasks, specifically for 5 classes B, T, D, R, and K, integrating both classification accuracy and regression precision within a single model. The justification for selecting Efficient Net B0 lies in its lightweight design, balanced scaling of depth, and reduced inference time. Efficient Net B0 represents a paradigm shift in model design, enhancing performance while substantially reducing computing requirements compared to predecessors like VIT and ResNet 50. Its core innovation lies in optimizing the trade-off between accuracy and computational cost, making it ideal for resource-sensitive applications without sacrificing predictive power. Our proposed architecture leverages transfer learning, using pre-trained weights from Efficient Net B0 trained on the ImageNet dataset. The process starts with a standardized input layer that receives RGB images resized to 224 by 224 pixels. This size balances capturing visual detail with maintaining computational tractability for subsequent layers. The backbone employs Efficient Net B0 as a powerful feature extractor. As image data propagates through its convolutional layers, the network progressively distills low-level features like edges into high-level semantic concepts. This process culminates in a dense 7x7 by 1280 feature map, encapsulating rich information about the image content. A global average pooling 2D layer then compresses this high-dimensional feature map. Unlike a traditional flattened layer, GAP is more robust and helps prevent overfitting. It works by averaging each of the 1280 feature channels into a single value, creating a compact one-dimensional vector of length 1280. This 1,280-dimensional vector is then processed through a fully connected dense layer with 256 units. This layer acts as a bottleneck, projecting features into a lower dimensional space to learn a more compact representation. The RealU activation function introduces critical non-linearity, allowing the network to model complex relationships within the data. To ensure robust training and prevent overfitting, 2 key regularization techniques are applied. First, batch normalization stabilizes the learning process by normalizing the activations from the previous layer. This is followed by a dropout layer with a rate of 0.5, which randomly deactivates half of the neurons during training, forcing the network to learn more generalized features. From this shared feature representation, the architecture diverges into multiple task-specific branches. This multitask learning approach is highly efficient. 4 distinct classification heads predict categorical outcomes for separate tasks, terminating in a softmax activation to produce probability distributions across 6, 5, 5, and 5 class outputs designated B, T, D, and R. In parallel to the classification branches, the architecture also includes regression heads. These are designed to predict continuous numerical values rather than class probabilities. Taking the same shared feature vector as input, these heads typically use a linear activation function to output unbounded values, such as bounding box coordinates or confidence scores, with at least one explicit regression output, K. The core building block of AIinNuclear is the Mobile Inverted Bottleneck Convolution, or MBC-conv. This highly efficient block consists of 3 stages: a 1x1 convolution to expand channel depth, a lightweight depthwise convolution to process features, and another 1x1 convolution to project them back down. This inverted bottleneck structure is key to the model's efficiency. The genius of AIinNuclear lies in its compound scaling method. Instead of scaling just one network dimension like depth or width, it uniformly balances all 3: network depth, width, and image resolution. For the baseline AIinNuclear B0, the scaling coefficients alpha, beta, and gamma are set to 1.2, 1.1, and 1.15, creating an optimally balanced architecture. The AIinNuclear B0 design is structured into 9 sequential stages built upon the MBE-conv block. The network begins with an initial convolution, then processes the input through these stages. As data flows, the spatial resolution decreases while the number of channels increases, concentrating abstract information into an increasingly rich feature representation. Integrated within the MBE-conv blocks are squeeze and excitation, or SE modules. These blocks intelligently recalibrate channel-wise feature responses. The squeeze step aggregates global information, and the excitation step generates attention weights for each channel. This allows the model to emphasize informative features and suppress less useful ones, boosting performance. Our training strategy was fundamentally anchored in transfer learning. We selected the AIinNuclear B0 architecture as our model's backbone, renowned for its balance of accuracy and computational efficiency. By initializing our model with weights pre-trained on the extensive ImageNet dataset, we provided it with a robust foundational understanding of general visual patterns like edges and textures. This pre-existing knowledge served as a sophisticated feature extractor, significantly accelerating the learning process. We employed a 2-stage fine-tuning protocol. Initially, the base layers were frozen to prevent overfitting and allow the model to utilize general image features from pre-trained weights. This locked the general features in place. Later, these layers were unfrozen and fine-tuned with a very low learning rate. This allowed the entire network to make subtle adjustments, refining the pre-trained features to adapt specifically to our dataset, providing faster convergence and improved accuracy. To ensure model robustness and generalizability, we applied 5-fold cross-validation. This technique provides a more reliable estimate of predictive power than a single train validation split. The dataset was partitioned into 5 folds. In each of 5 iterations, a different fold served as the validation set, while the other 4 were used for training. Each fold used 80% of data for training and 20% for validation. This systematic rotation ensures every data point contributes to both training and validation. The final performance metric was determined by averaging the validation loss across all 5 folds. The average loss L_AVG across folds is expressed as 1/k times the sum of L_k, where k equals 5 is the number of folds. By averaging, we obtain a single stable performance score that is less susceptible to the variance of a single data partition, providing a more trustworthy measure of the model's potential. To enhance generalization capabilities, we applied data augmentation techniques such as random rotations, zooms, and horizontal flips. This process artificially expands the training set by creating modified copies of images on the fly, forcing the model to learn underlying invariant features rather than memorizing specific examples. The augmentation transformations T_A applied to each sample. X created a diverse training set where Tx equals augment X, rotation, zoom, flip. Since our model handles both classification and regression tasks, we designed a multi-loss function to balance these outputs. The total loss combines classification losses for each output class using categorical cross-entropy, and regression loss for K using mean absolute error. Categorical cross-entropy is ideal for multi-class problems, while MA was chosen for its robustness to outliers. For regression, the MAA loss for K is calculated as the average of absolute differences between predicted and true values across n samples. The learning rate was carefully managed. The final learning rate was set to 0.0001 with a reduction schedule. This small initial rate is crucial for fine-tuning without corrupting pre-trained weights. The schedule gradually decreases the learning rate as training progresses, allowing for smaller, more precise updates as the model approaches the optimal solution. To handle its diverse tasks, Reactor Net uses a multi-headed output, Each classification output, B, T, D, and R, is assigned a softmax layer, ideal for converting raw model scores into an interpretable probability distribution. The regression output K is configured with a linear layer, providing the necessary unbounded continuous output for predicting a precise numerical value. The softmax classification prediction for Class 1 is defined using exponential normalization. This formula transforms the raw, unnormalized scores from the network, known as logits, into probabilities, where Z_I represents the logit for Class Y. To evaluate performance, classification outputs were measured using accuracy. The regression output K was evaluated using mean absolute error, or MEI. This metric averages the absolute differences between predicted and true values and was chosen for its robustness to outliers, enabling a comprehensive assessment of both discrete and continuous predictions. Test time augmentation is a powerful technique applied during inference to improve model robustness. Instead of relying on a single prediction, TTA creates a small ensemble of predictions from one model by introducing multiple, slightly modified versions of each test sample. This helps the model generalize to minor, real-world variations in the input data. We generate an augmented versions of each test sample. For our application, we use minor rotations of plus or minus 10 degrees to imitate subtle shifts in sensor perspective. We also apply horizontal flipping, which improves model robustness to symmetrical reflections in the thermal flux map, forcing it to learn orientation invariant features. Each augmented sample produces its own prediction. To derive a single, more reliable final output, we aggregate these results. For classification tasks, we take the mode, a vote for the most frequent prediction. For regression tasks, we average the individual predictions. This process smooths the output, reducing noise and leading to a more stable and accurate final value. For our classification outputs B, T, D, and R, the final prediction is the mode of the predictions from each augmented version. For our regression output K, the final value is the average of all augmented predictions, providing a stabilized estimate. By employing efficient net B0 as the model's backbone, our model achieves significant efficiency. This architecture uses a novel compound scaling method, resulting in a compact size of about 4.38 million parameters. This is remarkably smaller than older models, yet it provides robust performance. This balance of low parameter count and high performance is critical. It renders the model optimal for real-time and resource-constrained applications, like reactor parameter monitoring, where low latency is essential for operational safety and immediate response. Ultimately, the Reactor Net architecture successfully balances the competing demands of accuracy, efficiency, and real-world applicability, making it a powerful and practical solution for the complex, multi-output monitoring tasks found in nuclear reactor environments.
Welcome to For Science Salah Lotfy channel. In this video, we continue our exploration of a fascinating study recently published in Scientific Reports. The research introduces Reactor Net, a machine learning framework designed for real-time monitoring of pressurized water reactors using neutron flux imaging. Today, we'll focus on the performance results, model comparisons, and future challenges that define this important step toward AI-augmented nuclear safety. The study compared three state-of-the-art models, Efficient Net B0, Vision Transformer, and ResNet 50. The goal was to predict 5 critical reactor parameters: boron concentration, coolant temperature, coolant density, control rod position, and overall reactor reactivity. When we look at the results, Efficient Net B0 clearly outperformed both VIT and ResNet 50 across almost every task, achieving highest accuracy with values like 0.80 for temperature. For reactor reactivity prediction, Efficient Net B0 scored 0.49 MEI compared to 0.60 for VIT and 0.56 for ResNet 50. The researchers also introduced test time augmentation, or TTA. This technique enhances robustness by generating multiple augmented versions of each input during prediction. TTA works almost like an ensemble of models without training multiple systems, crucial for reactor monitoring where noisy data is common. Paired t-tests confirm these improvements weren't due to chance. In every case, differences were statistically significant with p-values well below 0.05. Still, challenges remain before Reactor Net can be deployed in a real nuclear plant. The dataset was simulated and may not capture every nuance of real operations. Real-time processing remains demanding, and interpretability is critical. operators must trust AI predictions in safety contexts. This study demonstrates that Reactor Net can predict reactor parameters with high accuracy. While challenges remain, this research sets the stage for next-generation AI-assisted nuclear monitoring. Thank you for joining us on this deep dive into Reactor Net. This research represents a major step towards safer, smarter nuclear energy. Stay tuned to For Science Salah Lotfy channel for more insights into breakthroughs shaping the future. Stay curious and stay safe. Welcome to For Science Salah Lotfy channel. Today we explore groundbreaking research that combines nuclear engineering and artificial intelligence to make nuclear power plants safer. In pressurized water reactors, control rods regulate power output by moving up or down, but monitoring their exact position in real time faces challenges like signal noise and delayed response. That's why this research introduces Reactor Net, a machine learning framework that identifies control rod positions with high accuracy in real time. Reactor Net processes operational data using advanced AI models that continuously learn from reactor behavior, making it more robust and reliable. This directly improves nuclear safety. Any delay in identifying rod positions could cause unsafe power fluctuations. By applying AI, Reactor Net reduces uncertainty and strengthens operator confidence in safety systems. This reflects a growing trend of integrating AI into nuclear power. The framework is adaptable and can enhance current monitoring systems. It provides operators with intelligent support tools that improve decision-making and situational awareness. As Professor Dr. Salah Lotfy from the Egyptian Atomic Energy Authority, I thank these brilliant researchers for their remarkable contributions to nuclear safety. Professor Dr. Ahmed Omar, Nuclear Engineering Department, Military Technical College, Kobry El-Kobbah, Cairo, Egypt. Professor Dr. Mohamed Elhadad, Department of Computer Engineering and AI, Military Technical College, Kobry El-Kobbah, Cairo, Egypt. Professor Dr. Momen El-Samra, Nuclear Engineering Department, Military Technical College, Kobry El-Kobbah, Cairo, Egypt. Professor Dr. Tarek Nagla, Nuclear Engineering Department, Faculty of Engineering, Alexandria University, Alexandria, Egypt. Professor Dr. Tamer Mekawi, Avionics Department, Military Technical College, Kobry El-Kobbah, Cairo, Egypt. Professors Ahmed Omar, Mohamed Elhadad, Tarek Nagla, and Tamer Mekawi have contributed equally to this work. Thank you to our dedicated viewers. Share your thoughts in the comments below. This is For Science Salah Lotfy channel. Let's keep exploring science together.